Okay, so our exam, test one, is next Monday. And lab. Okay. And Mahina, you can just put your homework there. Okay. The time officially is from 1:20 to 3:10. That's the official time. If you want to start this before here, that's fine. So let's say you want to start at like 12:30. Or maybe you go and pick up a sandwich or something to eat and then come and you can start it. I'll let you start it early. If you need to go a little bit late, I'll give you the time, but you're probably going to have to be sitting in my optics class. So you're going to hear me babble while you take your exam, just so you know. Again, I designed the exam to take an hour. And usually most people take about an hour and a half. And again, there's kind of a psychological barrier where you just have to hold on to your test and feel like it's safe to hand it in. And after you kind of cross that barrier, then you feel like you can hand in your exam. Again, there's going to be two parts. Part one will have 6 questions. Do any 5. You can do the question you didn't do as a bonus. They're going to be shorter questions. Whereas part 2, there's going to be 3 questions. You have to do all 3. And they're going to be longer questions, parts like A through D or something like that. And what's the material cover? It starts at the beginning and it goes up through and including all the projectile motion stuff in 2 dimensions, all the free fall and 2D and stuff like that. That makes sense? Okay. Any questions with that? Okay, so you have the practice exam, work through that. Again, I'm not going to hand out the solutions because then people just work through the solutions. But if you want me to go over with it, I'll over it with you, that's fine. But stop by my office, show me what you have. I want to see something on the paper. I just don't want to see something blank. I don't know how to do this one. Oh, I don't know how to do this one. Oh, I don't know. I will then kick you out and say no. I don't care. Work on it. I don't even care if it's right, but I want to see some blood, sweat, and tears on it before I give you a hand. Okay? Okay, new topic. We're going to start special relativity. This is not on the exam, not on exam. Okay, this will be on the second exam. And this topic is normally not done in general physics. I put it in there because a lot of people have some physics from high school, and I don't want anyone to panic. Don't panic. But I don't have my copy. We're not going to panic because I'm a professional. But I am going to pause and get my copy. Because we're not panicking. You handle that just like a profession. So the reason why I do special relativity is a lot of people will have physics in high school. And I start off right at the beginning, assuming you have nothing, so people can be a little bored with some of the material. And this way, you get to see something brand new and stuff like that. And we're not going to do anything more sophisticated than the Pythagorean theorem. Okay. So the question is, when was this done? So special relativity. Okay. Was done in 1905. Okay. And Einstein's general theory of relativity. Okay, I don't remember the exact date. It's like 1911, 1913, something like that. So let's say 1911, 1913. It's something like this. This one we're not doing. Okay. This is, if you want to know more about that, take my course in general relativity. We'll spend a whole semester on that. Does anyone know what this is a theory of? It's absolutely amazing. No? There's going to be a theory of gravity. This is a theory of gravity, and it basically states that there's no such thing as a gravitational force. that gravity is just due to the geometry of space and time, which is amazing. So basically the mathematics is calculus on a curved surface. So how do you take derivatives when your surface is curved? How do you do things on a curved surface? It's absolutely amazing mathematics. It takes me about almost half the semester to get the equations, but I set up every single little detail in the thing. But then you can look at black holes and cosmology and all these just absolutely amazing things. All the students have taken it, have all thought it was amazing. I've had engineers take it, they loved it. It's quite neat what you can do. We're going to do special relativity, which a lot of these ideas actually existed before Einstein. And then you can just put your homework there in that file. Okay. This existed actually, a lot of the equations existed before Einstein, but Einstein came along and actually gave them the correct interpretation. But this would have probably been done without Einstein. This, I don't know. I thought Einstein was the only one working on this, and it turned out there was a mathematician, David Hilbert, who was also working on it. But this is where Einstein being a physicist and Hilbert being a mathematician, Einstein had the edge. Hilbert forgot about some fundamental physics. Had the correct idea, but forgot fundamental physics. Einstein did not, and that's why they're called the Einstein equations and not the Hilbert equations. Okay, but what is this? So, does anyone know what you do in special relativity? I ask a very stupid question, or apparently stupid. Okay, what we're going to do in spectral relativity is we do the following. So in spectral relativity, we ask, how are the events? Let's say, how are the events as measured by the stationary observer and a moving observer related? Which doesn't seem very interesting. It turns out to be amazing. So let me draw a little picture and explain what I mean by that. I mean the following. Okay. Let's say I have a frame here like this. An x-axis, here's a y-axis, and this is stationary. This is a stationary frame. So maybe this is me. I'm just standing here, I'm stationary. Okay, now I'm going to have another frame over here. I call this the moving frame. And I'm going to call this frame over here that stationary S, and anything with a prime on it means it's going to be a moving frame. So I'm going to call this one S prime. So instead of calling this Y, I'm going to call it Y prime. Instead of calling this X, I'm going to call it X prime. So maybe this is my buddy in a car. And that moving frame is moving with some velocity v. Okay, so I'm here stationary, my buddy's in a car moving at a constant velocity. We see some event. This is some event. Okay, an event is anything that has a position in time. So this basically here, this event. So an event is anything that has a position and time. So this could be lightning hitting a tree. It could be a dog peeing on a fire hydrant. It doesn't matter. As long as there's a position and a time, it is an event. So what would my buddy over here say? If I'm the stationary observer and if I see an event, I'd say, oh, this occurred at some distance X. And then I'd measure the height here, Y. I'd say this occurred at some Y here, and I'd look at my watch. I'd say, oh, this occurred at time T. So this is what S would measure. What an observer in S would measure. Now, what about my moving friend? A moving friend would say, no, that occurred at some X prime here, some Y prime here, and the moving observer is going to look at their watch and say, it occurred at T prime. So the moving observer will measure X prime, Y prime, T prime. So this is what the moving observer would measure. And all you do in special relativity is say, how are these values here related to these values here? That's it. Nothing else. And again, you look at that and say, not very interesting. It turns out it's going to be amazing. Okay. Some of you have had physics in high school. How do you make a magnetic field when you're in high school? What does your teacher tell you? Make a magnetic field by, for example, let's say I put electric charge on here. I put electric charge on my marker. How can I now make a magnetic field? I throw it. A magnetic field is basically whenever you move charge, you get a magnetic field. Okay, so let's look at this. So I put charge on this, and if I put electric charge on this, this is going to have an electric field. If I throw it, I'm going to see a magnetic field. So I'm going to see an electric field and a magnetic field. That'd be me because I've just thrown the charge. Now, let's say my buddy is in a car, and my buddy is moving at the same velocity as the charge. What would my friend see then? Would they see a magnetic field? No, from their point of view, what is the charge not doing? It's not moving. If it's not moving, there's no magnetic field. So they would see an electric field. That makes sense? And so what happens, what Einstein was able to show is that there's a reason why we say electromagnetic fields. Is what Einstein was able to show is that electric and magnetic fields transform into each other. We're not going to do that in this course here. If you take my general relativity course or take my where I do it in there, or advanced E&M, we will show you how they transform. It's actually quite amazing how they work. But basically, electric and magnetic fields are the same thing. They just transform one into each other. And that's what Einstein was able to show with this really simple idea. Okay? So that's what we're going to do. And what we're going to do, we're going to show two things here. There's a lot of things. I'm just going to show you two things. I'll tell you what they are, and then I want to show you how they come about. So here's the two things we're going to do. Okay, so let's say this room is a rocket ship. Okay? And it's Monday, and I hand out the test to all of you. And I step out of the rocket ship, and I send you this way really, really fast. Let's say really close to the speed of light. And I say, look, I want you to look at that clock, and you only have 1 hour to take the exam. You know, I have my little binoculars, and I'm watching you. Okay, so I send you really, really fast this way. Again, I'm just standing outside. I'm on the ground, and you're moving this way really, really fast in the rocket ship. Okay, when I'm watching you, I'm going to notice something's actually going to bother me. First of all, you're going to have the same height as you had before. You're going to have the same width as you had before this way. But if I measure the depth of you this way, depending on how fast you're going, I'm going to see you actually get kind of small this way here. You could be traveling so fast that actually you would have the width of a piece of paper. So I'd contact you and say, you know, just so you know, your height is the same. Good. And, you know, this is the same. But you now have the depth of a piece of paper. But you would say, no, my depth is the same as it was. Nothing's happened. But then I'd also say something else. I say, here's the other thing, is I'm really sorry to hear that you're really thin this way. But not only that, you cheated. As I said, you only can take 1 hour for the test, but you all took 4 weeks. You know, there's no way you can say that 1 hour is 4 weeks. So you took 4 weeks to do the exam, and you're really, really thin. You know, and you would say, no, you know, you told us to take an hour, and that's all we took. We only took an hour for the test. Okay, one is called time dilation. The fact that you would say that you only took an hour to take the test, and I'd say you took 4 weeks. That's time dilation. The other one is that the fact that I'm going to measure you to be really, really thin in the direction of motion, and you're not, that's going to be called length contraction. And I want to show you how both of those ideas come about. It turns out they come about very, very easily. That makes sense? Now, there's other things too we could look at, but we're not going to, just because this is already getting kind of on the edge of what a general physics course should be. And that'll be fine. Okay, questions? So first of all, I want to set up things pre-Einstein. Because there's only going to be two assumptions we make in special relativity. And just so you know, invariably, there's always somebody who basically comes up with their own theory proving special relativity is wrong, and then quantum mechanics is wrong. And then they always contact their local physics department, which usually means me. And then they have their little theory about why special relativity is wrong and quantum mechanics is wrong. I mean, one happened just this summer where I was discussing with somebody who had the first time I've had a PowerPoint presentation. He had a like 35, page PowerPoint presentation on how he basically solved everything in the universe. Okay, so but I mean, the evidence for special relativity in quantum mechanics is beyond overwhelming. It's extremely well established. So let's talk about Galilean physics. Okay, this basically means pre-Einstein. Okay, so this is before special relativity. So let's go back to our stationary frame. This is X, and this is Y. And this is going to be at t equals 0. And at time t equals 0, I'm going to say the moving frame coincides with this. So at t equals 0, the moving frame and the stationary frame coincide. So in other words, here's this, and here's the moving frame. I'll put the moving, oh, it's black. I want a better black one. Let's see if this works better. That's better. Here would be my moving frame. I'll call this S prime. This is Y prime. This is X. Okay. And that moving frame is going to move with the velocity. So this is at time t equals 0. So if I look a little bit later on at time t, okay, my stationary frame doesn't move. It's stationary. This is me. My moving friend is over here. So draw my little curves. That's my moving frame. Okay. What would this distance right here be? If the two frames coincided before, and this is a constant velocity. This is a constant. What would that distance in between the two frames have to be? Doesn't look like 0. It's 0 over here. This is at t equals 0 to 0. At this time, this is moving with the velocity v. This is moving with the velocity v for some time t. That distance has to be what? V times t. Right? That makes sense? Okay. Now let's say here's something here. This is an event. So this person's going to say, that occurs at some distance here. Ooh, I used the wrong color. Oh, no. This person's going to say, that occurs at some distance here, x. This person's going to say, no, this occurs at some point, x prime. And this person's going to measure the y value. If I go like this person's going to measure the y for this. And this person's going to measure the y prime value for this. And this person's going to measure the event to occur at time t prime. And this person is going to measure that event to occur at time t. Okay, so if you were pre-Einstein, Galileo, what would you say about t and t prime? So they're the same, right? You're going to say t equals t prime. What about y and y prime? They're also the same. Now, with this one right here, what would you then say? If this is x prime, and this is vt, how are they all connected?
X. This means X.
Exactly. You say this distance here, x, has to be this distance plus this distance. So you say x prime equals x minus vt. And up here, I have y prime equals y, and t prime equals t. Boom. Those equations right here are called the Galilean transformation equations, because it transforms from one frame to the next. Okay, and you can go through about 99.99999% of your life using those equations, and those equations are going to work absolutely perfectly. Okay, there's a reason why relativity didn't come about till modern measuring techniques. Okay. Now, let's figure out something here. This object here might have a velocity. So I'm going to say this object here has a velocity here like this. So this is the velocity of the object. And the velocity of the object as measured by this person is going to be u. So u equals the velocity of the object as measured by s. Well, what do you think we'll call the velocity of the object as measured by this fellow? U prime. So u prime, this is going to be the velocity of the object as measured by s prime. Okay, let's figure out how u and u prime are related. We're going to get a result that I could write down the result, and none of you would say why. You would say, well, duh. But let's go through and do it formally. So let's take the derivative here of this equation. So I'm going to take the time derivative of this guy right here. Oh. So what is this? This is going to be dx dt. And what would be minus a constant times time? What would be that derivative? Just this right here. We just have the minus vt. You went the other way.
Oh.
It's just a constant, right? So this is going to be minus v. What does dx dt have a name?
V.
That's our velocity. In our case here, this is going to be the velocity of the object. And that's what we're calling u. So this is our u. This is our v. Okay, what do we know about t and t prime? They're the same, right? So I could really say that dt equals dt prime. So I can put this in here. Right, because this right here, this is the same as dt prime. Hey, does dx prime over dt prime have a name? It's the velocity of the object as measured by my moving point. So that's going to be u prime. So this is the velocity of the object as measured by the stationary observer. This is the velocity of the object as measured by the moving observer. Okay. Let me just, this can seem all more complicated than it need to be. Let me just show you how this works. Let's take an easy example. Then we can also see how that equation is going to break. And it breaks badly. Okay, so let's take an example here. Let's say I'm stationary here, and I have my friend who's in a car, and they're moving at, let's say, 30 meters a second this way. And I have my other friend here on a skateboard. My skateboard friend is coming at me 10 meters a second this way. Okay. So the question is, what are u and u prime? Okay. So who measures u? We have two observers, a stationary one, moving one. Who's measures u? The stationary. So I'm going to be the stationary observer. And what we're measuring is basically the skateboarder. This is our event, the skateboarder. Okay, what would I say then u is, just from this? Thing is coming to the left, so I'd say, oh, this is just minus 10 meters a second. Okay. Now, this is my moving observer. If you're in a car going 30 miles an hour this way, and the skateboarder is coming this way 10, if you're in the car, how fast would you say that skateboarder is moving at you? You'd say 40, minus or positive, or negative or positive? Negative. So this person would say minus 40. Okay. Let me show you this equation, see how it works. So what would you have? You'd have the u here, which is the velocity of what we're studying, minus 10. Minus v, this right here, this is our v. V is always going to be the velocity of that moving frame. This is our minus 30. So we're going to say this is minus 40 meters a second. Does that make sense? Questions? Now, let's say that we upgrade this situation here. So let's say my friend here gets a spaceship, okay? And my friend here also turns in then basically their skateboard maybe for the spaceship as well. Okay. So let's have an upgrade here. Actually, no, we're gonna tinker with it. But we're gonna upgrade this thing. So what I'm gonna do, well, let's go, we'll keep this in situation. So my friend is gonna go to a spaceship. And the spaceship is gonna be going at half the speed of light. Okay, so what's the symbol for the speed of light? C. Okay. So my friend with the upgraded car is going half the speed of light. My skateboarder friend upgrades to a spaceship. They're going this way at 3/4 the speed of light. Okay. The question is, what are u and u prime? Okay, so what's u in this case? Again, this is our moving. And this is our, I'll just say, put in quotes, event. Event is going to be whatever we're going to be studying. Okay, so what is u?
C.
Yeah, minus 3/4 the speed of light. Now the question is, what is u prime then? Well, we're going to use our little equation. Let's say u prime is u minus v. So our friend u is minus 3/4 c. Our v here is minus c over 2. Okay, got to get the common denominator, which is going to be I'll multiply top and bottom here by 2. So this will then give me minus 5/4 c. So this person, just like with the skateboarders, is going to say, oh, that this spaceship here is coming this way at minus, it's coming to the left at 5/4 the speed of light. Okay, now what we're going to find out is that when we do special relativity, it turns out you're not going to be able to exceed the speed of light. And so already, this is going to be one of the problems with this equation. This exceeds the speed of light. Now, we don't know why that's bad yet. We'll see a little bit this week. We'll see why we can't do that. But I want to show you why we can use this and actually come up with something that actually doesn't agree with the experiment. So let's do a variation on this. Is everyone happy with this so far? Let me show you. You could say, well, fine, you're just going faster than the speed of light. At this stage, that's fine to say that. We'll find out later on why we can't. But I want to show you why this approach actually violates an experiment. Let's do a variation on this. Okay, so let's say we have the following. Let's say I go and I have a laser here. I'm going to fire my laser this way. Okay, so a laser is nothing but light. So the light's going this way. How fast is it traveling then? Speed of light, c. Okay, and my friend with the spaceship is over here. They're going to be coming this way at half the speed of light. The question is, how fast will the observer and the spaceship see the laser light? Okay. So in other words, what we're going to do, this question is really saying find U prime. So here's our stationary observer. And here's our moving observer. Okay, how are these related again? It says U prime equals U minus B. Okay, so what is U in this case? Yeah, U is going to be what we're studying. We're studying light. So this is going to be C minus. Okay, V is going to be the velocity of the moving frame. In this case here, what's the velocity of our moving frame? Almost minus C. Here we get a common denominator and you get 3/2 C. The problem is this violates experiments. Okay. It turns out that you can do an experiment. I'm going to talk about that experiment. The experimental result is that all observers, doesn't matter who they are, measures the speed of light in a vacuum to always be c, no matter what you're doing. So we will see. That experiments show that all observers measure the speed of light in a vacuum to be c. Okay. So the problem is that those Galilean transformations violate this. So the conclusion is here. So therefore, the Galilean transformations do not agree with experiments. Those equations are going to be fine. They're going to work through almost every situation you're ever going to come across in your entire life, with the exception of when you start getting close to the speed of light. Close to the speed of light is about 10% the speed of light. Then you can start measuring you can start measuring errors in the equations. Not big errors, but you can start measuring errors. Okay. Okay, what's the experiment? Does anyone know what the experiment is? It's considered the most famous negative experiment in all science. In fact, the person who got the result didn't believe it. Because basically, he was getting this result and everyone knew this had to be wrong. Everyone knew that you had to have, this is what you should have found. And he got this, and he kept on trying to perfect his device, which he had actually perfected a long time ago. Now, as a result, it's still used today, the device. Anyone know who it is? Good double Jeopardy question. Michelson and Morley, there were two people. Okay, so the Michelson Morley experiment showed that all observers measure the speed of light in a vacuum to be the same. Show something else to be some more esoteric. So the device is actually this. This is actually the Michelson-Morley device. This is called a Michelson interferometer. It is still used today. In fact, I'm doing more and more work in glass research, and I'm working with actually Professor Colin Wilkinson's group. And I don't know a lot about spectroscopy, so I'm actually sitting on the spectroscopy course being taught. And there's something called infrared, Fourier transform infrared spectroscopy. And I didn't realize that a large part of that device is right here. This is actually still being used today. And in fact, probably most of you saw Interstellar, the movie. Okay, the actual science advisor for that was Kip Thorne. If you've ever had a chance to hear Kip Thorne talk, go and hear him talk. I've heard him speak twice. I actually heard him as a graduate, as a graduate student. He's actually quite old now, but he's absolutely amazing. He actually developed LIGO. Well, there were a lot of people, but I mean, he was the main consultant for LIGO. And that is basically this right here, this device put on really serious steroids. So imagine this distance here is actually several kilometers. Imagine this difference here is several kilometers. Okay, and what you can do is you can then measure what's referred to as gravitational radiation. And he got the Nobel Prize for this, but he was actually the science consultant behind Interstellar. That's why this, okay. With the exception of where they go into the black hole. Okay, with that exception. Okay. The science actually in the film is actually quite accurate. The black hole part, artistic license. Fine. Okay. So what do we do with this? It's a very clever device. So what I'm going to do is I'm going to do a top view. I'm going to draw this part of the view for it. And actually, I'm going to set it up like this for you. So the light's going to come in this way here, like this. So if I draw that, light's going to come in this way here. This is light. This is the top view. Okay. There's going to be a mirror here. And this is actually not a mirror. This is basically a glass plate. Okay. And what's going to happen here? Well, when the light hits here, part of it can be transmitted. So this is transmitted. And parts can be reflected. This is reflected. And then I'm going to have a mirror here. I'm going to have a mirror here. And that light's going to come up here, hit that mirror, come back down, hit here, come out this way. That light's going to hit here, reflect, come through, some will go that way, but also then parts are going to go this way as well. Okay, and so what's going to happen here is that these two light rays interfere. Basically, they can cancel each other out. Sometimes they can add, sometimes you can subtract. Where they add together, you get a bright spot. Where they subtract, you get a dark spot. And so what you can do here is you can look here and you're going to see basically stripes. You're going to see black and white stripes. Okay, it's a big deal. Now this is what you do. Here's the sun. And this is the top view of the Earth orbit. So the Earth's going to be over here. This is here. And a part of the orbit, we're going to be basically, we're going to be maybe our velocities like that. So there's going to be some part of the Earth orbit where we're moving toward the sun like this. Come over here, at some point over here, there's going to be some part of the orbit where we're like this, and we're moving away from the orbit. So part of it, we're moving, some component of the velocity is toward the sun, some part of the velocity of the Earth is away from the sun. What's going to happen here is that at the speed of light can change. If the velocity of the light in here changes, that's going to change the interference pattern here. So what's going to happen here is you basically set this up and you look at the interference pattern as the Earth goes around the sun. And what they notice is that no matter what happened, this interference pattern did not shift. And the only way you can get that happening is if basically, if you're moving toward the sun, you measure the speed of light to be c. If you're measuring away from the sun, you measure the speed of light to be c. If this is true, if this equation is true, what should happen here? The speed of light should be faster because the speed of light, the sunlight's coming this way, and we're moving toward it. So here we should see the speed of light going faster. Over here, the sunlight's coming this way, we're moving away, so we should see the speed of light going slower. So the speed of light should be going slower here, faster here. And when you work this out, that causes actually the pattern here to shift, and it did not. So the only conclusion is basically the speed of light here and here is the same. In other words, everyone measures the speed of light to be the same. You could say, well, fine. Okay. Einstein's genius was to take that result serious. Okay, most people, including Michelson thought that he messed up the experiment. So he spent a large fraction of his life perfecting this device, even though he had perfected it a long time ago. And as a result, we still use it today. It's used it. You can measure really, really accurate things with this to very, very small distances. Michelson didn't believe the result for a while. Einstein did, and once you take that result, special relativity pops right out. That makes sense? Okay, so what we're going to do, I'll set up the postulates for relativity, and then tomorrow we will get time dilation. Then on Wednesday, we'll get the twin paradox. You can't do anything with special relativity without talking about the twin paradox. You can figure out what the actual paradox is, because most people don't explain what the paradox is. They just talk about the effect, not the paradox. Okay, so Einstein uses the fact from experiment that all observers measure C to be the same. To develop special relativity. Okay, so let's set it up. So these are the postulates. There are only two postulates in special relativity. I use the word here. I want to make sure you understand it. What does the word postulate mean? It's being used in a mathematical sense. So if you have a postulate, what is it? Something you can't do with the postulate. You can't prove the postulate. It's basically it's not an assumption. It's basically what you're constructing your theory about. You can't use the theory to that basically then prove the postulate. So the first postulate is going to be basically taking the Michelson-Morley experiment serious. That's going to be the first postulate, that everyone's going to measure the speed of light to be the same. Again, I can't use special relativity to prove that because it would be circular reasoning. I'm using the experimental, the experimental result. So the first one, all observers measure the speed of light in a vacuum 2BC. Okay. Let me set up the second one, then I'll talk about the next one. The next one sounds kind of awkward. And then we'll call it quits for the day. Postulate 2. If two observers are moving at, let's say, with a constant speed relative, well, let's say velocity, relative to one another. Okay. It is impossible for either observer to do an experiment to determine which observer is moving. I'm just going to leave it at that. I'll explain it tomorrow. I'll give you some examples, and we'll see. This is going to resolve something for us. I'll explain what that means, because right now you look at it and go, okay. Have a great day. See you this afternoon.